Hello everyone, my name is Diksha and I am from the Bodhi Academy. Today I am going to discuss some basics from D and F block elements chapter of 12th standard, and along with that we will also solve some questions, okay, important questions from that chapter. Okay, now D and F block elements, in our periodic table we have four different blocks S, P, D and F. So today we are going to study the D and F block elements. Okay, D block elements are also called as transition elements. Okay, so D series or D block, they are also known as transition elements. Now there is one reason why they are called as transition elements. First of all, they have incompletely filled d orbitals. So d orbitals are not fully filled. That is, we have almost every element in d orbital is having partially filled d orbital, but there are some exceptions. So in this chapter we are also having some exceptions, so you have to be ready for that. That is zinc, cadmium and mercury. These are the exceptions because they are having fully filled d orbitals. Okay, so these are not considered as the transition elements. So these are not transition elements. Okay, then next thing is the general configuration of D block, that is N minus 1, D 1 to 10, NS 1 to 2. So this is a general electronic configuration of D block elements, all the D block elements. If we start from scandium, scandium is the first D block element that is having number 21, atomic number is 21, and configuration goes from like this: argon 3D1, 4s 2. Okay, now according to the filling of orbitals, the 4s2 will get filled first and then later on d will get filled. Okay, so 3d1, 4s2 scandium, then accordingly we are having all the configurations from scandium to zinc, then later on the next 4d series, 5d series, we are going to have some configuration that we will not discuss here in detail because we have to solve the worksheet. So yeah, and here another next important thing is their trends, how they vary across the period, how they vary across the group, and atomic size, oxidation state, then their characters, their different properties. Like D block elements or the transition elements, they have different properties. For example, they have catalytic property, they have magnetic property, they can form colored compounds, interstitial compounds. So there are different properties which are followed by these elements. Okay, so we will start with the solving of worksheet. We will take up the first question. So first question is, why is the outer electronic configuration of chromium 3d5 4s1 instead of 3d4 4s2? Okay, so chromium, the question is chromium configuration is argon 3d5 4s1, and why it is not chromium 3d5 3d4 4s2. Okay, so the question is why it is like this and why it is not like this. Okay, because we say that s orbital get filled first and later on d orbital get filled, but here we can see that s orbital is having only 1 electron and d orbital is having 5 electron. So why this is so? So we will see the answer now. Now chromium, let us write the configuration in the orbital form. The diagram we will draw. So chromium, argon is a noble gas, so we will leave that. Then we will write the D block. So D block is having 5 orbitals. So 1, 2, 3, 4, 5, and then S. Okay, so actually if you go accordingly, meaning from scandium to zinc, or if you start from scandium, we see that all the elements, they are having 4s filled orbital, but here we see that we are having s incomplete orbital. So here the configuration looks like this: 1, 2, 3, 4, 5 and 4s1. So this is 3d, this is 4s. And if you see this, if we are having 4s2 in chromium, then it looks like this. 4s2 and 3d4. Okay. Now if you see now here, for chromium, when it is having 3d4 4s2, 4s2 is filled, but 3d4 to when you are having one electron in the fifth orbital, what happens here? It is half filled stable configuration. Okay, 3d is half filled stable configuration when you will get one more electron here. So what happens here? This one electron from here, it is transferred to this orbital. Okay, because if you achieve stable configuration, if you achieve the noble gas a half filled stable configuration, it is more stable. So to attain the stability, the electron from this orbital is transferred to this orbital. Okay, so that's why we are having 3d5 4s1 instead of 3d4 4s2. So the reason, the answer of this question will be, first you have to draw the configuration, and then you have to write that chromium is having 3d5 4s1 configuration to attain the half filled configuration because of the stability. Now to attain the stability of the orbitals. Okay, so the main reason is to attain the stability. Okay, so that's why we are having this configuration. Now next question is, what is the trend in oxidation state of transition metals? Okay, trend in the oxidation state. Okay, now if you see the transition in transition metal, the oxidation state trend, it looks like this, meaning if you go from scandium, it will be having +3, then titanium +3 +4, vanadium. So if you see now, from scandium to zinc, there will be first +3 +2, meaning you will get only 2-3 oxidation state. So first you will get less oxidation state. Then if you reach manganese, which is in between, manganese you will have total 6 oxidation state. So first there will be less oxidation state, then manganese you will have more, then again there will be less oxidation states when you reach zinc. Okay, now why this is so? Now the reason is because of unpaired electrons. Okay, because if you see from scandium there is one unpaired electron, titanium there are two. So if you see the number of lone pairs or number of unpaired electrons, they goes on increasing first, and when they reach manganese, then again they start decreasing. So this is the reason we have this trend in oxidation state. First it increases, then it decreases. Okay, so this is about the trend in oxidation state. Next question is, all compounds of scandium are colorless. Give reason. Okay, scandium, they are having colorless compound. Now we know that scandium shows which oxidation state? It shows only +3 oxidation state. And scandium in +3 means what is the configuration? See, normal configuration of scandium is argon 3d 3d1 4s2. This is a normal configuration of scandium. If scandium is showing +3 in its compounds, then +3 means we are losing 3 electrons. So 1, 2, 3. 3 electrons we have lost. So we are left with only argon. So scandium +3 is having only this configuration, argon configuration. That's why it is not having any lone pair. And to have a colored compounds, or when D block elements or transition elements, when they give color to a compound, they should have at least one lone pair. Okay, and they should have at least one unpaired electron. So that is the reason, since we have no unpaired electrons here, this is a stable configuration, so we are having the scandium compounds, they are colorless, they are not having color. Okay, then next question, copper plus is colorless while copper 2 plus is colored. Okay, this is also based on the color. So copper plus is colorless and copper 2 plus is colored in an aqueous solution. Okay, so why this is so? Let us see the configuration of both the ion. So copper plus means what? Copper configuration is argon 3d10 4s1. So plus 1 will be what? Copper plus 1 means argon 3d10, and copper plus 2 is what? Argon 3d9. Okay. So if you see, the first copper plus is a stable configuration as it is having fully filled d orbital. But copper plus 2 is having not, this is not fully filled. Here there is one unpaired electron. So this is not fully filled. That's why since we are having unpaired electron, this will show color. This will give color to the compound, and this is colorless. Copper plus is colorless. Okay, so this is the answer. Next question here is magnetic moment of manganese chloride is 5.92 Bohr magneton. Gives a reason. So next question, magnetic moment of MnCl4 2 minus is 5.92 Bohr magneton. Now there is one formula to calculate this magnetic moment. So let us see that formula. Magnetic moment is denoted by mu, which is equal to root of n plus 2. Okay. Now this formula we require unpaired electrons. So let us see here magnetic moment of MnCl4. So our transition element is which? Manganese. So we have to see how many unpaired electrons we have in the manganese. So for that first we have to see the charge on manganese. Okay. So charge on manganese we will calculate. So manganese we will consider it as X plus chlorine. Chlorine is having what charge or what oxidation state? -1. So -1 into 4. How many chlorine? We have 4 chlorine is equal to this 2 minus, because we are having this as a overall charge. So this will give us X minus 4 is equal to -2. So X will be equal to -2 plus 4, which is equal to +2. So we got charge on manganese as +2. Okay. Now let us see the configuration of manganese. So manganese, normally the configuration is 3d5 4s2. Okay. Argon 3d5 4s2. Now if we have +2 means what? Losing of electrons. So losing of electrons, it will achieve this half filled configuration, that is argon 3d5. So Mn plus 2 will have argon 3d5 configuration, and these 2 electrons will be lost. So from this what we come to know? We come to know that we are having total 1 2 3 4 5 orbitals. So 1 2 3 4 5. We fill like this, you will see that there are 1 2 3 4 5 unpaired electrons in the orbital. 5 unpaired electrons you have to put here the number. So you will have 5 plus 2, which gives us 5 into 7, which is root 35, which is approximately 5.92 Bohr magneton. Okay, which is 5.92 Bohr magneton. So the reason here is, first you have to write all this configuration and this formula and find out the answer, and then you should write, since it is having 5 unpaired electrons, it is having so and so magnetic moment, because magnetic moment depends on the number of unpaired electrons. Okay, so this is the simple answer of this question. Now next question is based on the ionization enthalpy. Okay, the first ionization enthalpy of chromium is lower than that of zinc. Okay, so this answer also depends on the ionization, on the electronic configuration of the particular element. First ionization enthalpy of chromium means what? To remove the outermost first electron, the ionization enthalpy required is lower. But for zinc it is more. Okay, so first ionization enthalpy of chromium is lower than that of zinc. So chromium, what is the configuration? Argon 3d5 4s1. Okay, now tell me, and zinc we have argon 3d 10 4s2. Now tell me, yeah, here 4s1 we have one electron that is in the outermost shell, and here we have two electrons, okay, in this orbital. To remove one electron will be easy, or to remove this if you have stable configuration or fully filled configuration, to remove electron from this is easy, or to remove electron from this is easy. Obviously the one which is having one unpaired electron, that electron to remove it is easy. So here in chromium it is quite easy to remove the first electron, so ionization enthalpy required is less. But this is having paired electrons, okay, 4s2 paired electrons. So to remove the electron from the paired orbital or the paired electrons, it is not very easy. That's why here ionization enthalpy is high than this, okay, than chromium. So if you see here, everything depends on the ionization enthalpy, everything depends on the electronic configuration of the elements, okay. So you have to know the electronic configuration, especially of 3D series, okay. So if you know this, you will be able to solve most of the questions from this chapter, D and F log elements, okay. Okay, so these are some of the important questions that we have discussed just now. So you have to practice more from this chapter, meaning there will be some other questions which will be also asked on other trends. Now we have just discussed about ionization enthalpy, oxidation state, so they might ask on atomic size also. Then I will discuss one from atomic size. So if you see, if you see from 4D to 5D, if you go from 4D to 5D, that is from one group to second group. Now what we know, that if you go down the group, more shells are added, so atomic size increases. But if you go from 4D to 5D in this series, the size is not increased, it remains almost same. Now this is suppose 4D electron series, this is 5D, then this size, the elements from this series and this series, they are having almost same size. Now what might be reason here for this? Now this is because due to poor shielding effect, for 4f electrons, okay, 4f electrons or 4f orbital. So in this 5D we will get 4f orbital. So 4f orbital, what they do poor shielding effect. Poor shielding effect means what? If we have nucleus and we have shells, okay, then this shell, this first shell, this is a first shell, this is a second shell, okay, this is a third one. If this third shell is suppose our F shell, okay, and after that also we are having one shell. So what happens if you are having d electrons in this shell, okay, then this nucleus will not be able to actually the nucleus won't be able to attract this shell electrons towards itself more easily or more with more more strongly. But when F electrons, they are providing poor shielding effect. Poor shielding means what? Poor screening effect, which does not act as a good screen. So what happens? This will be able to hold them more tightly towards itself. So if the nucleus is holding outermost electron or attracting outermost electron towards itself more easily, then what happens? The size is not increased, size will decrease due to the attraction, okay. And the reason that here is, main reason is poor shielding effect from f orbital electrons or f electrons, okay. So this is also an important concept from this chapter that is going to come. Next one thing is lanthanoid contraction, that is also important. Lanthanoid contraction means the same thing that causes due to the shielding effect. So here definition is very important. So the definition is what is lanthanoid contraction? The gradual decrease from lanthanum to lutetium in their atomic and ionic radii due to the poor shielding effect. It is called as the lanthanoid contraction. Okay, so this is very important. Yeah, and then about actinoids. Actinoids, there are no much questions which will be asked during exams, because there is nothing much in that chapter, but some configurations can be asked, applications can be asked, and also their uses, like actinoids, there most of them are radioactive elements. When they are forming, you will not get them, meaning the half life of these elements are very less. Okay, so that's why there is nothing much on this elements. And actinoid contraction, that is also the same as lantanoid contraction. Okay, so some of the definitions, and this the questions are from their properties, characteristic properties. Okay, then D block elements, they have tendency to form interstitial compounds. Then they have also tendency to form, they also act as a catalyst. Okay, then colored compounds. So these are some of the characteristics. Okay, so this you have to remember. Okay, so with this we will finish this solving of worksheet. For next video we will come with another worksheet. Okay, so yeah, thank you.